Well, thank you everybody for attending. My name is John Briand, and I'm going to be presenting pile load testing for Pier pile reuse in Boston. I'd like to thank the co-authors of my original paper on this project, Douglas Agajan and Mike Schultz. So initially, I'm going to be getting into the project background and subsurface conditions. So the project, as you can see here in the project site, as you can see here in the lower right corner, is located in East Boston, Massachusetts, with the pier situated in Boston Harbor, directly across from downtown Boston. The pier is the site of a former one-story naval warehouse and distribution facility that included 3 railroad spurs, 1 that ran along the center of the pier, and then 2 that you can no longer see on each side of the pier. At the locations of the railroad spurs, you see a much tighter spacing along those alignments due to the heavier loads than the main warehouse facility itself. As you can see in the photo highlighted down here, this is part of an overall development by the developer that we work with on this project to develop 7 total properties, 4 of which were going to go on the pier itself, and 3 of which went on the backlands. Previously, we had completed 3 of the buildings prior to starting on the Pier 1 foundation program. And so for those 3 buildings, they were built between 2006 and 2018 with a break for the financial crisis. The foundations for the buildings were 14-inch driven square concrete piles, and they were driven down into the glacial till and weathered bedrock layers that were below the fill and Boston blue clay. At this site, as I'll discuss a little bit later, these piles were driven a little bit deeper than what will happen for the pier, as the thickness of that Boston blue clay layer is much greater than in the actual harbor itself. So getting into a little bit of a history of the pier itself, the picture here on the right shows the pre-existing conditions from the early 2000s after the warehouse facility had been demolished, as well as some existing structures on the waterfront. This area was ripe for redevelopment. And so not only did the single developer for this property, but other developers have begun building luxury apartments right on the water due to the amazing waterfront views of downtown Boston. The pier itself was founded on driven 14-inch diameter concrete-filled steel pipe piles. However, similar to most piers of this age, it's difficult to find detailed design data about the piles themselves, as well as any pile installation criteria. And so during design, we had no actual idea of what loads were installed to. However, we do know what the building footprint was, and so we were able to back out an approximate pile capacity and assume that these piles were installed well over the required capacity compared to what the actual service loads for the structure were. The one item that we were able to find was an as-built pile location plan that showed the embedment depths of all piles across the entire footprint, as well as the test boring data from the original 1950s investigation that had a total of 9 test borings spread across a 3x3 grid. Additionally, during our initial preliminary design, we also drilled 8 borings around the exterior of the structure, including 3 on each long side and 2 on the short side, to help us confirm the previous installation data. Based upon the as-built pile location plan, we were looking at pile pier tips between about 95 and 135 feet below the pier deck. And using the previous and existing information, we overlaid the subsurface profile with the pile locations and determined that all of the piles bared in either the glacial till and or weathered rock. So looking at the subsurface conditions, you can see here on the right, we have an initial subsurface plan from our preliminary design back in 2012. For that, you see a very typical profile of what you see in Boston, with fill that has been backfilled to gain additional land in the harbor, Boston blue clay, the glacial till, and the weathered bedrock. The fill itself was about 5 to 30 feet thick and consisted of soft silts. The Boston blue clay, as you can see in the figure on the right, had mostly weight of hammer material, which you would expect, and ranged from about 30 feet at the inside of the harbor to about 90 feet deep at the sheet pile wall. Then finally, you get into your bearing strata, which are typical of this region, where you see glacial till with very dense sands, gravels, and fines with mixes of cobbles and boulders in some locations. And that layer was about 70 to 120 feet below the pier deck. And then finally, your weathered bedrock that consisted of highly weathered fractured siltstone. And for this image that you can see on the right, it shows both weathered rock and bedrock. This is a preliminary figure. And once we did a detailed evaluation of the rock cores and did some unconfined compressive strength testing, we determined that this was more of a weathered rock layer that was coreable. And so we redefined that in our final report to weathered rock. And this was encountered anywhere from about 100 to 130 feet below the pier deck. So getting into the development of our load testing program, we had to look into the building code for the criteria for the reuse of the existing piles. And since this project is in Massachusetts, they have a slightly more strict building code than many other states and commonwealths and have supplements to the actual building code itself. In general, there were 4 requirements per the building code: to not adversely affect the piles by the demolition, that the piles are structurally sound. And as you can see here in the image on the right, there was significant corrosion over the 7 decades that these piles had been installed, at least at the water line, that they have adequate structural loading capacity, and that it meets all the requirements of the building code. So teaming with our partner, McLaren Engineering, who was the structural engineer on the project, we performed a 3-phase program to determine feasibility of reuse of this pier. The first phase was a structural inspection of the existing piles above the mud line that included using dive teams to look at the piles below the water surface, as well as teams in boats and to view the piles above the water surface. Once the structural team was able to finish their inspection, they went into the development of a structural pile repair plan that I'll go into a little bit more detail on later. And then finally, we performed our load testing program, which is really the main point in this presentation. So we'll go over the structural inspection a little bit quickly. And so for the steel casing corrosion zones, the structural engineer identified 4 specific zones, 2 of which were the most severe locations. And these involved areas that you saw a lot more wet and dry cycles than the other zones. So the splash zone was the most severely corroded, where the 1/2-inch thick steel casing was corroded to as little as 1/8 of an inch in some locations and at least 1/2 an inch across the entire splash zone. And so this was, we had seen this in the majority of the piles. And as you can see here in the upper right-hand corner, the corrosion was pretty severe and could potentially affect the structural capacity of the final elements. Additionally, in the mean low water zone, we saw similar severe corrosion, with corrosion of typically between about 0.2 and 0.3 inches, so about 40 to 60% of the pile of the steel thickness. And then finally, we get into our tidal and mudline zones that had less corrosion since there were less wet and dry cycles of these, but we did see marine growth due to the fact that both of these areas were below the typical water line. So for the structural pile repair plan, you can see the repair plan prepared by the structural engineer on the right here. The repair was determined to be conducted in both the splash zone and the mean low water zones, where we saw typically greater than 50% corrosion of the pile itself. For these corrosion zones, the repairs were prepared for a 75-year design life for these structures. And the repair itself consisted of demoing the existing pier deck and pile caps, removal of the loose corrosion and growth in these tidal zones, which consisted of air blasting above the water level and water and sand blasting below the water level. Upon completion of the cleanup of the pile itself and removal of that loose corrosion, we installed 18-inch diameter, 1/2-inch thick steel pipes and sleeves over the existing piles. And then the annulus between that was grouted with concrete and with grout and packers in order to have a quality seal between those piles, and was tested by the structural engineer. And ultimately, the structural pile repair for these repairs was 300 kip capacity. So now I'll get into the geotechnical considerations. So the first consideration we had was what type of load testing we wanted to conduct that was economical for the project, since this was more of a feasibility study prior to a final design to determine if the entire pier was capable of being reused. And so for the static pile load test, we looked and saw that our typical factors of safety were 2.0 per your usual IBC. But one of the main factors that led us to not use the static pile load testing was that we would have to either include 4 reaction piles, which would consist of demoing out the deck at 4 additional locations for each test pile, or use a large dead weight across the entire structure. And so due to both cost concerns with having to remove additional sections of pier deck and time constraints potentially with that as well, we determined that static pile load testing was not proper for this project. Next, we went into the dynamic pile load test, which is obviously typical of most of our projects that use driven pile foundations. For this, because we're in the state of Massachusetts, or the Commonwealth of Massachusetts, and the building code requires a factor of safety of 2.5 due to the dynamic load test is not considered a direct measure of pile load, very similar to the AASHTO codes. And so for this reason, and due to the concern that we may have some issues with some of the piles themselves due to their age, we determined that we wanted to use both dynamic pile load testing in combination with rapid load testing in order to reuse the piles without significant issues should loads be close to what we're looking for the design loads. And therefore, we ended up deciding that we would use rapid load testing. And for the rapid load test, you can see here we have these reaction masses here that totaled about 33 kips for this project. We ended up using these reaction masses in the rapid load testing test frame in order to conduct our dynamic load tests. Additionally, for the rapid load tests themselves, we were able to use a building code factor of safety of 2, since this was a direct measure of the force imparted upon the pile, and that it's a very compact load test setup and mobile test frame. And so for schedule concerns, we were actually able to conduct one series of dynamic and rapid load tests per pile per day. And so we were able to do the actual load testing within 3 weeks. So for the pile top preparation, we saw cut a 6x6 foot opening in the deck and then cut off the pile below the concrete deck about 1 foot. Divers then completed their repairs of the actual pile itself and then installed a 2-inch thick steel plate that you can see here in the blue that was welded to the top of the pile that was able to impart the force over a uniform area so that we didn't have any issues during the pile load testing. And then the installation equipment itself was brought up with your typical pile extender, cushion, and follower. So getting into the actual pile load testing program, we had a 2-phase program since we did not know if this was going to be an economically feasible project. And so the first phase was just to determine whether or not these piles could potentially be reused. And because both the owner, who is Massport for this project, and the developer, Roseland, did not want to pour a significant amount of money into a load testing program should the piles be beyond repair, it was determined that we do an initial program with 2 test piles that would consist of loads of 200 kips, which was the minimum financial feasibility for the project, and 240 kips that allowed us to gain some efficiencies and reduce the cost for both the owner and the developer. And with this, we determined that we would use rapid and dynamic pile load testing at each individual pile location. And the purpose for this was that should we end up needing to use the dynamic load testing, that we could correlate the test results between the rapid and the dynamic load test to hopefully get a factor of safety of 2 should we need that additional capacity out of the ultimate loads. Once this was complete, obviously, since we're presenting on this topic, we ended up having a successful phase 1. We went into the detailed evaluation. And the purpose of the detailed evaluation was to do more of a parametric study across the entire pier footprint instead of 2 individual locations to make sure that the pile capacities were acceptable, not only in the areas where we had the deepest embedment into the glacial till and weathered bedrock layers, but also shorter embedments in those layers, shorter piles versus longer piles and things of that nature. And so for this particular portion of this, we ended up doing 3 loading intervals, 200, which was the base load that we had discussed before, the 240, which resulted in some cost efficiencies, and then ultimately the 300 kips, which was the maximum load that the structural engineer permitted per their design. And so for this program, to save some money, instead of doing the rapid load testing at all 10 pile locations, we determined that we would do it at the first 2 pile locations and then do dynamic testing only at the 8 remaining locations in order to save money from the setup of that rapid load test itself. So getting into the results of the program, for the phase 1 load test data, we used sonic echo method testing initially just to determine if there were any significant defects in the pile. And should there be a significant defect in an individual pile location, we had alternate locations to go to that we would address at that time, but we did not need that for the phase 1 program. One item of particular note for the phase 1 program was that we ended up getting a pile tip reflection from the sonic echo method testing for test pile 2 that corresponded to the approximate as-built pile tip elevation within plus or minus 2 to 3 feet. We did not see that at test pile 1. However, it did not note any significant defects, so we moved forward with that test. So in particular, the results showed that the dynamic load test ended up getting about 350 to 400 kips allowable for the 2 piles. And that is obviously well in excess of the 300 kips we were looking for. And part of the reason for this is because we were using the dead reaction masses as our driving force. We ended up using 6, 12, 18, and 24-inch height intervals for the drop weight. And so the 18-inch increments were slightly below the required load of the 300 kips. And so we ended up increasing it to 24, which significantly increased the load imparted on the pile. And we backed that off in the phase 2 investigation. Additionally, for the rapid load test, we hit our 240 kips in the second test pile, and we're just slightly under, less than 1% in the first test pile. So these results gave us confidence that we could move forward into phase 2. The pile sets, when we look at those, were less than 0.1 inches, which would indicate that the piles were driven into the soil and weathered rock, and probably did not have their full resistance mobilized, since we did not see significant movement. So some of the overall conclusions from the phase 1 were that with the dynamic pile load testing, we were actually able to exceed the full structural design loads by up to 33%. For the relatively low pile deflections and sets, it was determined that we can likely get additional geotechnical capacity out of this location, or out of these piles themselves, and that the piles reuse was feasible, and we could move on to the phase 2 pile load testing program. So for the phase 2 pile load testing, similar to phase 1, we performed the sonic echo method testing across all of the piles. One good thing to note was that we actually were able to see that 9 out of the 10 test piles that we had toe reflections within plus or minus 2 to 3 feet of that as-built pile tip location plan. So it shows you that the records from this previous location, or from the previous data, were actually fairly accurate. In addition, we did not see any significant pile defects that were associated with these piles. So getting into the load test results themselves, for the piles with the dynamic load testing, we saw between about 270 and 375 kips of allowable load based upon the factor of safety of 2.5. And I'll get into on the next slide a little bit of why we didn't get the 300 kips in every pile. And then for the rapid load test, we were able to get 360 kips and almost 400 kips of load, which proved again that we had significantly little defects in these, or that we had significant capacity out of these piles. For the pile set itself, test pile 4 was the one anomaly where we got up to about 0.3 inches of movement, which is still well within the limits for this structure. And for that, you should note that we tested that pile in the rapid load test here to about 400 kips. So that's about 30% higher than the design load, which obviously makes sense that we're getting some additional movement. And then the remainder of the pile, similar to phase 1, ended up seeing sets of less than 0.15 inches, indicating that they could achieve additional capacity. So diving into the dynamic load test a little bit, 4 out of the 10 piles achieved their design load of 300 kips. However, 6 out of 10 did not. For 3 of the test piles, we were within 5% of the ultimate load and within 10 kips of that required load. And so as you can see there, we can definitely understand that these piles would well exceed the capacity required. For the remaining 3 test piles, 4, 5, and 7, we were a little bit lower, about 10 to 11% lower than the ultimate load. And the main reason for this was because we had such high loads in phase 1 with the 24-inch drop height that we did not want to overstress these piles and lose any monetary contribution to the final structure that the owner would realize. So for the pile sets in general, these were less than the 0.3 inches as discussed. And so in our final report, we determined that these were lower bound estimates of total capacity and that we could get significantly higher loads. So getting into the final conclusions, the soil and weathered rock resistance were not fully mobilized, as we can see through the PDA data. When we looked at the PDA data, as you would assume with the Boston blue clay, it did not have a significant contribution to the actual pile capacity, and that the glacial and these piles were likely driven both into the glacial till and through into the weathered bedrock due to their low pile sets. One other main component here would be that if we did end up testing these piles to a higher load cycle for the rapid load test or a higher stroke height for the dynamic load test, that we would see significantly higher loads. But for a project like this, you may be, and other projects, you may end up seeing capacities that are limited by your structural design and not your geotechnical capacity. The one other item that I would like to note before I get to the acknowledgements is just the overall cost for this program. So the total cost for the pile installation itself, or the pile load testing itself, was approximately $1 million. And for the phase 1 program, since we had the initial mobilization and setup costs, it was about 1/3 of that total. And for the phase 2 program, it was about 2/3 of that total. And just gives you an idea of the order of magnitude for this testing program. So just wanted to get into some final acknowledgements and show an image of what one of the final renderings may be. So the owner of this project was Massachusetts Port Authority. The developer was Rosen Residential Trust. And then we worked hand in hand with the structural engineer, McLaren Engineering Group, on this. And then finally, the dynamic and load testing firm was Geosciences Testing and Research of North Chelmsford, Massachusetts. And the SEM and rapid pile load testing were AFT out of Florida. And I would like to note that for a project like this, we ended up working fairly closely with the 2 testing companies in order to get approval from Massport for our modified testing program. And so for projects like this, it is definitely good to have an overall design team that works well together and not just stay in your silos. So